In this module, we will complete our discussion of the valence bond treatment of hydrogen molecule using quantum mechanics. And at the end, we will also compare the two treatments, especially valence bond treatment and molecular orbital treatment in regard to hydrogen molecule. As you already remember that we have already obtained the energy expression for the valence bond treatment in case of hydrogen molecule. In the case of hydrogen molecule, we constructed the approximate wave function using valence bond treatment and then obtained the corresponding energy using variation method. The energy is given by the expression EA is equal to integral psi valence bond He cap psi valence band d tau divided by psi valence band d tau. Here psi valence bond is the wave function which we constructed under valence bond treatment, and this is equal to C1 psi Ha1 psi Hb2 plus C2 psi Ha2 psi Hb1. This psi Ha1 psi Hb2 we can take as psi 1 and psi Ha2 psi Hb1 we can take as psi 2. Therefore, the wave function for the hydrogen molecule under valence bond treatment becomes C1 psi 1 plus C2 psi 2. Here you already know that psi Ha and psi Hb, they represent basically 1s atomic orbitals of the two hydrogen atoms, A and B respectively. And C1 and C2 are the two coefficients. Taking into account this valence bond treatment, we derived the energy expression in our earlier module, and we showed that EA is equal to C1 square alpha 1 plus 2 C1 C2 beta 1 2 plus C2 square alpha 2 divided by C1 square plus 2 C1 C2 S square plus C2 square. Here, if you remember, alpha 1 is integral psi 1 He cap psi 1 d tau, and this, it was shown in the earlier module, is equal to 2Eh plus Q. And similarly, alpha 2 was also shown to be equal to 2Eh plus Q. Here Q, if you remember, we did it in the earlier module that this Q is equal to integral psi A H1 psi Hb2 H prime cap psi Ha1 psi Hb2 d tau. Also, if you remember, we found out that beta 1 2 is equal to psi 1 He psi 2 d tau, and that was equal to 2Eh S square plus A, where A is equal to the integral psi Ha1 psi Hb2 H prime cap psi Ha2 psi Hb1 d tau. Now, the energy expression was then simplified by minimizing the equation with respect to the coefficient C1 and C2, and you remember we got two equations, A which is C1 then alpha 1 minus EA plus C2 beta 1 2 minus EA S square is equal to 0. And we had another equation which we call as equation B, which is C1 beta 1 2 minus EA S square plus C2 alpha 2 minus EA is equal to 0. These are a pair of algebraic equations, and from them, if we make an assumption, because the two hydrogen atoms are identical in all respects, we assume that alpha 1 is equal to alpha 2 is equal to alpha. And similarly, we assume that beta 1 2 is equal to beta 2 1 is equal to beta. So, from these one can get the energy expressions EA plus, that is the energy which is equal to alpha plus beta divided by 1 plus S square. and Ea negative, which is alpha minus beta 1 minus s square. So all these derivations we have done in our earlier module. But we have yet to find out the values of the two coefficients C1 and C2, which ultimately make up the valence bond wave function. So now let us try to find out the expressions for the coefficients C1 and C2. The equation, if you see, which is the equation for Ea plus, if we substitute this equation in our equation A, about which we just mentioned, we get the following equation: C1 into alpha 1 minus alpha plus beta upon 1 plus s square bracket closed, plus C2 brackets beta minus alpha plus beta upon 1 plus s square bracket close is equal to 0. Now if we simplify this equation, you can see that ultimately we get C1 is equal to C2. That means the two coefficients are equal. In an identical way, if we substitute in equation A, then one gets this equation: C1 alpha minus beta upon 1 minus s square bracket close, plus C2 brackets beta minus alpha minus beta upon 1 minus s square bracket close is equal to 0. If we solve this equation further, here we get C1 is equal to minus C2. Earlier we had got C1 is equal to plus C2. So basically what we derive from here is that C1 is equal to plus minus C2. So this is very, very important, and that is the relationship between the two coefficients. You can see that we can very easily get the values of the two coefficients using the normalized wave functions. And as you can see here, this is the normalization condition, and from the normalization condition, as you can see, once we put C1 is equal to C2, then the value of the each coefficient comes out to be C1 is equal to 1 upon 2 plus 2 into 1 plus s square under root, and the same will be the value of C2. But if we put the condition C1 is equal to minus C2, then we get the expression C1 is equal to 1 upon 2 into 1 minus s square under root. So the two coefficients C1 and C2, which we defined earlier and from which the corresponding valence bond wave function was constructed, their values have been found out. In one case, that means one will be the case for the bonding orbital where the energy is lower, one gets C1 is equal to C2 is equal to 1 upon 2 into 1 plus s square under root. And for the other orbital, which would be higher in energy, anti-bonding, that will be C1 is equal to 1 upon 2 into 1 minus s square under root. Now in the next part, we will go into the details of the integrals Q and A, which we have already defined. We will see what do these integrals ultimately represent. As you can see that Q is equal to integral psi HA1, psi HB2, H prime cap, then psi HA1, psi HB2 d tau. Whereas A is equal to integral psi HA1, psi HB2, H prime cap, psi HA2, psi HB1 d tau. Now let's take each one of them and expand it. But before doing that, let's go back to our electronic Hamiltonian for the hydrogen molecule. This we have already studied in our earlier module. And you know that He prime can be written in the form He prime is equal to HA1 prime plus HB2 prime plus H prime cap. And here, if you remember, we discussed that Ha1 and Hb2 are the Hamiltonians of electron 1 and in atom Ha and electron 2 in atom Hb respectively. And H prime was the corresponding Hamiltonian part, which consists of these four terms. One is E square upon 4 pi epsilon 0 R1b minus E square upon 4 pi epsilon 0 R2a plus E square upon 4 pi epsilon 0 R12. This R12 and this term, which is positive, this is the term representing electronic repulsion. And the last term is plus E square upon 4 pi epsilon 0 R, which represents the nuclear repulsion. So if we substitute this expression for H prime cap in our expression for Q, as you can see here we are doing, we get four different terms. If we simplify and we know the fact that psi HA and psi HB are normalized, therefore Q becomes this, and Q is minus integral psi HA1 E square upon 4 pi epsilon 0 R1b then psi HA1 d tau minus integral psi HB2 E square upon 4 pi epsilon 0 R2a psi HB2 d tau plus integral psi HA1 psi HB2 E square upon 4 pi epsilon 0 R12 psi HA1 psi HB2 d tau plus E square upon 4 pi epsilon 0. So these are the four terms which we are getting. The first term in this expression represents the interaction of charge density of electron 1 around nucleus A with nucleus B. The second term, if you closely examine it, represents the interaction of charge density of electron 2 on nucleus B with nucleus A. The third term is representative of mutual Coulombic interaction energy of two electronic charge densities. And the fourth term, that is the last term, represents nuclear-nuclear Coulombic interaction. Since the interpretation of terms in this is possible only via Coulombic interaction, therefore this Q is also referred to as Coulomb integral. Exactly on the similar lines, one can go into the details of the expression for A. Here you can see again there are four terms and we are substituting and expanding it. And since you know atomic orbitals are normalized, you know that, and overlap integrals are representing the overlap also, we have seen here already. Here also you can see that we get here four terms, but the integrals in the above expressions, all these four, cannot be interpreted in the manner similar to that of Coulomb integral. This is because in this expression for A, the wave functions considered recognizes the indistinguishability of the two electrons. It is therefore a strictly quantum mechanical entity. Since the exchange of an electron between two nuclei is considered in this expression, therefore it is called exchange integral. Therefore you have seen that from our detailed analysis that Q and A are known as Coulomb and exchange integrals respectively. Now after having done this, you can see now that our energy expression is given by EA plus minus, that is equal to 2EH plus Q plus minus A divided by 1 plus minus S square. So from here one gets the corresponding expression for the binding energy, which is equal to, as you can see, binding energy means the energy which the hydrogen molecule possesses in comparison to the energy of two isolated hydrogen atoms. And as you can see, delta E plus minus comes out to be equal to Q plus minus A upon 1 plus minus S square. And if we plot this versus internuclear distance, we get this plot. Experimental plot is shown, and then the theoretical plot, delta E plus and delta E minus are shown here. From this diagram, you can very well see that delta E plus describes a stable chemical bond, and delta E minus describes unstable chemical bond. The minimum of delta E plus versus R curves occurs at a distance of 87 picometers and with the corresponding energy of 305 kilojoules per mole. Now, after having done the valence bond treatment of hydrogen molecule, and we have also earlier done the molecular orbital treatment of hydrogen molecule, let's have a look at their comparison. If you remember it, for hydrogen molecule, the molecular orbital for a hydrogen molecule using molecular orbital treatment is given by phi A MO is equal to psi HA1 psi HA2 plus psi HA1 psi HB2 plus psi HB1 psi HA2 plus psi HB1 psi HB2. Now, if you look at the first term and also have a look at the last term, these two terms psi HA1 psi HA2 and psi HB1 psi HB2, these are called ionic contributions because they represent both electrons of hydrogen molecule on one atom. On the other hand, if you look at the term psi HA1 psi HB2 and psi HB1 and psi HA2, these represent covalent contributions because these represent a situation where one electron is around one atom and the other electron is around another atom. Thus, one can say, after looking at the molecular orbital wave function, that it is a wave function in which there is a combination of both ionic and covalent contributions, and this contribution is 50% each. There are two terms which represent ionic contributions and two terms which represent covalent contributions. So, this is a very important result regarding the molecular orbital treatment. That means it's an equal mixture of ionic and covalent terms. Now, in contrast, if you look at the valence bond treatment, in the valence bond treatment, the wave function psi Vb is given by psi Ha1 psi Hb2 plus psi Ha2 psi Hb1. That means these are the two terms. Let's look at the terms only. We are not taking into account the coefficients here. You can see here that these two terms psi Ha1 psi Hb2 and psi Ha2 psi Hb1, these are the covalent terms. They are representing the corresponding covalent contributions. So, as such, in this there is no ionic contribution. However, another possibility is that instead of considering that one electron is on atom A and other is on B, one can also say that both electrons are on atom A or both electrons are on atom B. So, in that case, the wave function will have some ionic contribution as well, and that ionic contribution will be psi Ha1 psi Ha2 plus psi Hb1 psi Hb2. Therefore, one can say in a very general form that the total valence bond wave function under valence bond treatment can be taken as a mixture of covalent terms and ionic terms. We considered in our discussion and calculations only covalent terms, but there could also be ionic terms, and one could see how much is their contribution. So that totally there will be four terms: psi Ha1 psi Hb2 plus psi Ha2 psi Hb1 plus psi Ha1 psi Ha2 plus psi Hb1 psi Hb2. Overall, if you look at these two treatments, they appear to be different approaches to chemical bonding, but both these are basically similar in terms of construction of the approximate wave functions. Also, you must have seen that the results which are obtained using these two treatments are in good synchronization with each other as well as with experimental trends. So I think these are some of the important points which one must keep it in mind. There are, of course, there are many similarities between valence bond treatment and molecular orbital treatment. For example, both of them account for the directional nature of the bond. In both of them, bonds are formed by the overlapping of the orbitals. And we have also seen that there are certain differences also, because in valence bond treatment, bonds are localized to two atoms, but that's not the case in the molecular orbital treatment. And atomic orbitals are generally monocentric, but molecular orbitals are not. Those could be polycentric, and in the case of hydrogen molecule, they are over two centers of hydrogen atoms. So you can see very well that there are quite a few differences in the two approaches, but ultimately both valence bond treatment and molecular orbital treatments, they are two different approaches to explain chemical bonding in the molecules. And that is how quantum mechanics successfully explains chemical bonding in molecules, and that we have shown by taking the example of hydrogen molecule. To summarize our discussion, we have seen that the valence bond treatment of hydrogen molecule, we have completed that discussion. We have found out the values of the two coefficients C1 and C2, which ultimately help in completely defining the wave function under valence bond treatment. We also went into the details of the Coulomb integral and exchange integral and explained their significance. They all contains 4 terms, as we saw, and we also saw that exchange integral is a quantum mechanical concept. It cannot be very easily explained using classical treatment. And lastly, we also compared the salient features of the valence bond treatment and molecular orbital treatments. These two treatments may appear to be rather different approaches to chemical bonding, but they are quite similar in terms of the construction of the approximate wave functions. And we see both of them to a great extent reasonably explain the corresponding experimental values obtained in the case of hydrogen molecule.